So, basically, we so far considered two options. One was privately estimate some quantity that effectively governs our sensitivity. And then you don't need to guess anything. You add noise that scales with that sensitivity, but you paid extra privacy for estimating that quantity. Then we said, oh, well, let's not estimate it. It's too expensive. Let's just figure out if we're in a good enough regime or not. That works, but it has the disadvantage of, unless you guess correctly what is your regime, you are either gonna deny the reply and just give up because you were hoping, you were too optimistic, you hope that the sensitivity is lower than your data, or you were too pessimistic and then you added noise that scales with that pessimistic quantity. So the third option sort of interpolates between the two. I would not go into the proof because it's somewhat involved, but here's the intuitive idea. Oh, I see. I think a few things were missed here. There are like a few plots that were lost. Wait, let me move. Maybe here I have them. No, yes. Okay, so these two we saw. Okay, so, sorry, yeah. Okay, so first of all, I'm changing the order, but just so we see. So, in those more tricky mechanisms, I'll no longer be able to show you the ROC because this is no longer a analytically expressible code. So what we have here is privately estimating the mean, the sum, privately estimating the numerator, and then computing the ratio. So we have two distributions, and as you see, it's from privacy perspective, it's nearly perfect. Again, I can't say for sure because maybe there's a slightly better auditing technique, maybe there's slightly worse data sets, but it looks quite good. But the problem was that, as you see, the accuracy is met. Second one was, as we did, this was proposed test release. Now the distributions look the same, practically, because I added noise that's way more than I needed because I was somewhat pessimistic. So again, everything looks the same. And now we get to the third one, which is smooth sensitivity. Okay? So here's the idea of smooth sensitivity. What did we say? We said that the sensitivity itself might be a sensitive variable, so we have trouble. But what if I have a different value, a function of the data, that upper bounds the local sensitivity and is smooth? What do I mean by is smooth? Has this property that changing one element doesn't change this quantity by much. So a low sensitivity upper bound of the local sensitivity, in a way. That is the idea. If I have this quantity, this function, then I can sample from a distribution that with noise that scales with this smooth sensitivity and no longer worry because I know that my distribution wouldn't change by much by changing one element because yes, my center changed a little bit, but that changed by less than the local sensitivity. And then my noise also changed, but not by much because the noise depends on the smooth sensitivity, and the smooth sensitivity itself has low sensitivity. Okay? That is similar to the two-step algorithm, but the difference is that I didn't pay extra privacy for estimating another quantity. I sort of paid extra privacy for moving from local sensitivity to smooth sensitivity, which is somewhat more pessimistic. So I always have to pay somewhere, but I either pay by estimating another quantity or by estimating privately my guess whether the optimism of not being too sensitive is correct, or by scaling my noise not with the true local sensitivity by some upper bound on it. So here are the results. So again, it looks practically perfect because this is somewhat pessimistic analysis and it's better. And it looks, again, about the same thing. Like, things are not very impressive. Yeah, now that I think about it, moving between these notebooks, I also slightly changed the settings. Okay, anyway. In the same setting, this is what we get. So you see all three distributions. Sorry, there are four distributions here. This is the estimate versus the real distribution using four valid methods. Method one is using the global sensitivity. And this is this line here. That's so terrible, that's like orders of magnitude larger. And all three are the noisy counts, meaning estimating the sensitivity directly, the proposed test release, and the smooth sensitivity, and they're like, look about the same. But they look the same. That's not telling the real story because that depends on what is the regime of your actual sensitivity. So here's just one plot out of many possible ones, and I'm not even sure how to show the variability here. So here's what happens. Proposed test release has this weird phenomenon where you say, my noise is relatively small throughout, but until I get to this point with high probability I completely fail. So when I succeed I'm good, but with high probability I fail. So it's not really fair how to compare it. This is estimating the count privately, and this one, the dashed green line, is the smooth sensitivity. So it seems like the smooth sensitivity is worse than just doing the naive thing, but then here it gets a little better, and annoyingly again I changed settings. So here you can see this difference that here there's a certain regime where the smooth sensitivity does get slightly better than the estimating directly the noise, because the count, because I'm not really releasing both of them, I'm just releasing one in a way that takes care of the other in a way. Right? So the somewhat annoying conclusion I want you to draw from these plots, and again I will try to organize them to tell a more coherent story, is that we have a few ways to attack it. None of them clearly dominates the other ones. And it really depends. So if you think you have a very good guess of your sensitivity, maybe you should use proposed test release. If you think that estimating another parameter, the sensitivity parameter, won't be much harder than maybe just estimate it directly. If you can do the smooth sensitivity and things don't blow up, if you have a smooth sensitivity that's relatively close to local sensitivity, use that. But basically, the overarching story is the same. If your sensitivity is not too sensitive, then you're okay, because either one of those methods will work. And if your local sensitivity is very sensitive, then you're doomed. Then you'll probably have to scale with the global sensitivity regardless. This is what I want you to take out of it. And notice that all of this sophistication could have come about because we moved away from some very naive statistics such as mean estimation, where the mean has the same local sensitivity regardless of the rest of the data set. It doesn't matter what's your data set, adding or removing one element that is an extreme element will have a significant effect, the same significant effect, not only a significant effect. But once you move to somewhat more sophisticated statistics, things become more complicated. Okay? Now, I would move on to the other techniques, but I would like to express some discomfort with this last section because it's a bit eclectic. It's a bit of here are a few more things. And why am I doing it here? Because this lecture is covering basically the way I think of it is previous lecture was like even moments and quantiles, the most basic quantities, are somewhat challenging. And the next lecture will be like, okay, let's say I want to create some predictor, like very basic linear regression or logistic regression or something like that. So now this lecture is like, what if I want to ask a question, estimate a quantity that's like one step more complicated than the most naive ones and less than like already real like estimation problems. Regression, prediction problems. So we saw this toolkit of local sensitivity, which is something that's typical to somewhat more complex questions, and how can we get something out of it. And then there are a few more. So I just want to mention them here, and we will reuse them again later. So one is report noisy max. We sort of discussed it before. Here is one of the most natural things to do. Say we would eventually want to predict something like the salary, and we want to know which of many features is a better predictor. Or we want to know which of several groups is more present in the population. Like I don't even know what is the most dominant race in this area. So I'm like, okay, I have a histogram, how many people are white, Latino, black, etc. And I want to know what's the maximum one. And we mentioned it in this last lecture, but just want to mention again. I can add noise to all bins, and the noise doesn't have to scale with the number of bins. Why is that? Because when I change a single element, I change a single bin. It was either added or removed to one bin because every element is allocated to one bin, or two if it's substitution, I remove from one. But there is a subtlety here, because if you just add noise to every bin and you don't do anything else, then your privacy doesn't degrade with the number of bins, but your accuracy degrades with the number of bins, right? Because have sufficiently many bins, the probability that one of the smaller bins will just get a very large amount of noise starts growing. It grows logarithmically typically depending what type of noise you added, but let's say you added Laplace noise. Yes? So you have a union bound, but still, at some point, you have infinitely many bins, and only one of them has, let's say you have one bin that's 100 and all the rest are either 0 or 1. If you have enough bins, one of them will add so much noise that will surpass the 100. So what we do is we do truncated histogram. We do a histogram, but we also truncate any number before we add the noise. Any bin that has less than 5 values will be truncated to 0.
Doesn't that theoretically cause the case where, say there's a bin with 4 and a bin with 5, a bin 4, or the case where the bin is 5, it's now the bin has some chance, now the bin has no chance.
Right. But if the chance was anyway extremely small, then you're covered by the delta. Exactly. But then you need to reason about the gap. Like that is how generally speaking, what is the accuracy? Right? So here's this is basically I'm moving to the next step. So what's interesting about report noisy max is two things. One is, hey, sensitivity looks terrible, but then it's not. But also accuracy somewhat like in the median case, has to be rewritten. Because if you require that accuracy will be that you will report the correct max, then you won't be able to do it if the second one is extremely close to the first one. So typical accuracy guarantees for report noisy max are something like the probability of reporting someone decreases proportionally to the gap between the one we reported and the true maximum. And then you say, well, if the maximum group has 1 million users and then this one has 990,000 whatever, so like, yes, that's not the maximum one, but it's a good candidate to be the second one. And also, again, going back to statistics, if this data set was sampled from a larger one, then indeed there's a case that one. Okay, so again, this is another example where we need to consider the accuracy notion more carefully. Right, and here this is the example where it's going to be practically the same. Next thing is, notice that in the above threshold, in the proposed test release, I told you proposed test release is a recipe. It's not an exact algorithm. Why? Because the recipe says make a guess of the local sensitivity and then check if the actual sensitivity surpasses that threshold in a private manner. But how do I do it in a private manner? So one of the most natural things to do is above threshold. What is above threshold? Above threshold is to say, if I have a guess for the value of a function, what is it? And then I can say, well, is it significantly above it or is it significantly far away from it, right? Because then I just turn it into an absolute value. Where will this be relevant? So a few things. And then how would I do it? That's natural. Again, I'll add noise to the query and we're good. But above threshold has the following interesting property. Above threshold has the option of issuing many queries and yet paying only for one. Right? You calling. So above threshold has the following deal. If you have a stream of queries and you think most of them are, let's say, small, notice it doesn't matter what the value is, because I can always say I have the query and I have a guess. So the query that I issue is actually what is the difference of the statistic from this guess in absolute value, maybe, or something like that, right? Then I can issue many queries, and I will pay only for the stopping point. So if I stop once there's a single failure, I'm only epsilon private, right? The way I do it is I add noise to each of the queries, and I also added noise to the threshold. Why is that relevant? So, in a way, you can think of what I did in proposed test release above threshold, but a single above threshold. But you can sometimes even do better things. It's like you issue many queries, you think most of them are low sensitivity, so you can continue with like an above threshold, and you stop by the first non-sensitive query. And again, we know that we can do sparse vector, which is like we do composition and then have it many times. We can also see how it's relevant to something that we already did, which was how did I make the guess? So remember I said in proposed test release, I guessed some local sensitivity, and then I used it to move on. How do I make the guess? I have some prior, right? So in the example of the cells, I said, well, men and women, it's about 50-50. So with high probability, the smallest group will have at least 400 or 450 people. How did I know it? I had a prior about the world. So the prior in many cases is modeled as I have a public data set that I know is close to the private one. So let's say I have the census from a decade ago. I have statistics about the entire country, but I don't have about this specific city. So the private data is this specific city, and the public data is the entire population. So I have a good guess. So now I can do things like above threshold, etc. And in one practical example where we see it in these days, and it's becoming more and more common, is in the context of LLMs. Because typically we treat the data that is used to train the base LLM as public. Is that justified? I wouldn't say so. But this is the fact of the world. We basically say if it's already out on the internet, tough luck. Yes, that doesn't mean that everything's okay, etc. This is not a lesson that discusses the moral aspects of privacy, but in practice, this is how people treat it. If it was already released on the internet, you're good. And it's also not true that the foundation model is typically really trained only on public data from the internet, give or take. But even more importantly is, like, many people say, yes, maybe that's really terrible that the company is trained on that data, but like that's out of my control. My problem is that now I want to do fine-tuning on some private sensitive data. Now I care about this sensitive data. So I have this medical data that I want to fine-tune the model on. Yes, maybe the big tech companies train their data, their models on their foundation models on someone else's sensitive data, but that's his problem, it's not mine. So however you look at it, the task of looking at fine-tuning as I have a foundation model that gives me a good guess, but not a perfect guess, which is why I need the, because if the foundation model can predict perfectly everything on my private data, then I wouldn't do fine-tuning. It's already good enough. No, it's not necessarily, no, but it's maybe that my data is not unique in any way. Maybe I have my own private collection of pictures of cats and dogs that I took. But they are so clear and high resolution, and the animals are so typical, it's not like some weird breed, that the foundation model will be able to perfectly predict. Again, I'm mixing here LLMs and classification, but just for simplicity. So but then I wouldn't fine tune because my data doesn't have any extra information. So I assume I have some private information I want to fine tune. So fine tuning is a great example where the foundation model has a good guess typically, right? Because typically you don't fine tune on something that the foundation model doesn't know anything, because then it's no longer fine tuning, it's nearly training. And the result is that we can do all sorts of things like above threshold, etc. That what happens is basically the closer, like, we have this weird trade-off where if the original guesses are far away, then we will fail very quickly because the privacy will run out of privacy budget. If the original guesses are very close to our data, we haven't learned much. And there's like this in-between sweet spot where we have an incorrect guess just ever so often, and then we pay the privacy price every time we need to correct it. But it happens rarely enough that we can teach it many, many steps, and we just basically show it, look, you're give or take correct, but here you have a mistake, corrected here, you have a mistake, corrected there, and then we're good. This is basically the typical setting where this kind of things occurs. So to summarize, the challenge of this week is that, unlike most of the other weeks, I don't have an overarching story. This is more, here's a toolkit. And there's one component of the toolkit that's well defined, which is we wish to scale with the local sensitivity. We can't do it directly, but we can do other tricks. And another one, which is take this spirit of not necessarily asking the straight, direct, simple question. Don't necessarily do accuracy that is the naive definition of accuracy, etc., but like retell the story and do things in a slightly different manner, and then you're good. So for example, maybe you do report noisy max, and then you know which subsets of the population are bigger, and then when you move on to the next step where you want to guess the size of the subsets, you already have a good guess because you did report noisy max for a few times, right? After you can always peel a few subsets. So you did report noisy max. Oh, white people are the biggest cohort group in this population. Okay, the next one, Hispanic are bigger, etc. And then for that one big one, you can ask the noisy max. To estimate the sum or the count, and that then you have a better accuracy because this is the bigger group, and then you can do that kind of stuff step by step and combine it in various ways. And again, like I chose to show comparing the gap between averages, but sometimes people compute the ratios. Like you don't ask what is the difference between the average salary, but what's the ratio of the salaries. And there's an endless stream of different settings, and this is where exactly you finish the course, things seems like very simple. Oh, we have these tools, they solve everything. You get into the real world and everything gets messy. And in a way, from next week on, I will start telling a somewhat more positive story, because luckily for us, there is one algorithm that is now basically the way any machine learning is done these days. And once we manage to solve running that algorithm in a private manner, we basically have again a tool that can solve many, many problems at once, instead of like calibrating at every point like the different needs. Okay, I think we should stop here unless there's questions.